All right, so we'll get started. I was just joking before I turned the video on that there's a lot of people missing, so I guess the people who are not here, did so well in the test that they don't need to come to class. I wonder if that's the case. Now, if you're, studying the video because you have other obligations, I understand that, and that's okay, but, it is important to try to keep up with the material because there is new material, right? So, in any event, we're in chapter 5 now, which is rational expressions, equations, and functions. So I'm just going to dive right into it. So let's just do a little review of fractions. What do you guys know about fractions? For example, if I wanted to add 3/7 plus 2/8, what would I do? How do you add fractions?
Make the bottom the same.
Make the bottom the same. Find a common denominator. So for this one, what do? We look for the least common multiple of 7 and 8, which is what? Just 7 times 8, right? I mean, there's no common factors here. Nothing really to do. So what you do is 3/7 times 8/8, right? Plus 2/8 times 7/7, right? And what we got? We've got 24/56 plus 14/56. And now that we have the same denominator, we can add them, right? So what's 20? So we got 24 plus 14/56. What's that? Yeah, 38. 38/56. Can we reduce that? They're both even, right? So we can divide the top by 2 and divide the bottom by 2. What do we got? 19/28, I think. There you go. Now, was this the best way to do this calculation? Like, what could I have done differently that would have made this easier? What didn't I do at the beginning that I could have done? Like, are both of these fractions in quote-unquote lowest terms? What does it mean to put fractions in their lowest terms? It means to cancel any possible factors from the numerator and the denominator, right? 2/8, that's 1/4, isn't it, right? 2/8 is 1/4, right? So 2/8 is 2 times 1 over 2 times 4, right? So I can cancel these 2's, and I get 1/4. So I could have looked at this as 3/7 plus 1/4, right? And just to get straight to the point, the way to do those is you do 3 times 4, right, plus 1 times 7 over 28, right, 7 times 4. So I'm abbreviating the calculation in the blue, right? I wrote out all the steps in the black. I'm just being a little bit more to the point here in the blue. That's 12 plus 7, which is 19, so we get 19/28, right? So making a simplification of the original fractions can make the calculation easier, can't it? How do we multiply fractions? You guys remember? So if we have like 3/7 times 10, 39, how does that work? We multiply fractions, we multiply the numerator times the numerator and the denominators times the denominator, right? So this would be 30 over, big number, 7 times 39, that's 210 plus 63, it's 273, I think. Can anyone confirm or deny that?
The one right above that, you got 3, 4 plus 1, 7. Why are the 4 and 7 on top?
All right. So what I'm doing here, I'll write it in red. How about that? So his question is, why did I make that middle step there? So going from here to here, this is a general algebra step we can make. So like a over b, right, plus c over d. All right, so what we can do, the lazy way to add fractions is just to multiply the first one by d over d, right? We multiply the second one by b over b. And see, by doing that, that gives us the same denominator both places, right? So what we have then is a times d plus, let's say, b times c divided by bd, right? So what's going on here is you're multiplying, what's the pattern there? You're multiplying this one, right, up on this, right? And you're multiplying that one on that, right? And that's the pattern here. A times d, b times c. This is sometimes called cross-multiplying. So we can cross-multiply to make, to have the common denominator just be the product of the two denominators like that. And that's what I did here. See, I did 3 times 4 and 1 times 7. And then downstairs, I have 7 times 4, which is 28. The reason this is okay is because you're multiplying the first fraction by 1, the second fraction by 1 in such a way that you're making them have the common denominator. Here BD, but the specific example, 28, 4 times 7. So we'll do another here in a second. I'll come back to that. I need to finish the example I was working on here, but it's great that you asked a question. No problem there. Can you guys tell me what I did, in some sense, what's a better way to do this example? I've got 30 over 273. That's kind of a mess, isn't it? What could we have done to make this easier? How about this? This is 3 over 7, right? We could have thought about how does 10 factor, right? How does 10 factor? It's 2 times 5, right? How does 39 factor? Well, it's 3 times 13, isn't it? So you see, to make life easier, I could have thought about the prime factorizations of the numbers, and I could have taken the preemptive step of canceling any like factors before I multiplied. That would have made my life easier, wouldn't it? See, the 3 here and here cancels, right? And I'd actually just get what? 10 over, what's 7 times 13? It's 91, yeah. So indeed, this right here is an equivalent fraction, right, to 30 over 273. If you reduce 30 over 273 to lowest terms, you get 10 over 91. Right? So I'm just trying to remind you of some tips and tricks for how we do arithmetic with fractions. So the one issue is to add fractions, we have to give them the same denominator, right? Other things we can look for is how do we reduce fractions, right? Looking for common factors we can cancel. Multiplying fractions, we multiply the top times the top and the bottom times the bottom like that, right? So let me just write, so this is just some general algebra rules, if you will. I'm going to rewrite what I wrote here a second ago. Just keep it in mind. If we're adding a over b plus c over d, we can do a times d plus b times c over bd, right? That's a way to add fractions. And if we have the product of a over b, and I'll say times x over y, just use different letters here, how about that? That's ax over by, right? Are there any other, what if I had subtraction? It would be the same, right? I could put plus or minus on the top, it wouldn't change anything. Here's another one. I'll do some examples of this one next. If we had a compound fraction, right? If we had something like a, I'll use this notation, over b, divided by c over d. So this would be the same as this, a over b, divided by c over d. So a fraction of fractions. Notice I try to draw the middle bar longer so you can clearly see which one is in the middle as opposed to top and bottom. Well, the way to simplify such a fraction is what? I'll work it out here, right? I could multiply this by what? If I multiply that fraction by BD over BD, what happens? I get A over B times BD upstairs, right? Over C over D times BD downstairs. How does that simplify? So on the upstairs expression, the b's cancel, right? B over B cancels. What do you have upstairs then? A times D, right? And downstairs, the D's cancel, right? So we've got C times B, right? So this is one of my go-to simplification rules. A over B divided by C over D is equal to A times D over B times C. Notice this only works if it's a single fraction upstairs and a single fraction downstairs. If there's an addition in the numerator or an addition or subtraction in the denominator, you can't just do this. You have to think through it more completely, all right? We'll see examples of that. Here, let me give you a numerical example of this. If I have like 3/7 divided by 1/2, what do I get? So if I follow the pattern, I get 3 times 2, right, over 1 times 7. I get 6/7. Another way to put this is division by 1/2 is the same as multiplication by 2. All right? Let's do some slightly more complicated examples here with numbers. Now, everything I'm doing so far, you could do with a calculator, right? So like, why are you doing it? Well, I'm doing it because all of the steps that I'm making are the same steps we have to make when we're working with fractions of polynomials, all right? Which is what chapters 5 and 6 are about. They're about how do we deal with rational expressions. A rational expression, we're going to see it's like a polynomial divided by a polynomial, right? So we're going to work on how to work with those. One more numerical example, though, before I get to it. How about this? What if I had something like 13 over 80, plus 17 over 100? Now, in this case, I mean, I could just cross multiply, right? But then my new denominator would be what? It would be 80 hundreds, which is, what's that? Is that 8,000? I can't do math. 8,000, right? So I really don't want to do that. What I want to do instead is ask, what's the least common multiple of 80 and 100? Right, least common multiple. Least common multiple, because that's the smallest common denominator I can make here is what it is, right? So the way to figure that out, at least the way I figure it out, I mean there are other ways, but 80 is what? It's 8 times 10, right? Which is really 2 times 2 times 2 times 2 times 5. Those are your factors, your prime factors of 80, right? How about 100? Well, that's 10 times 10, right? Which is 2 times 5 times 2 times 5. So the least common multiple, we should be able to see from this. What's the least common multiple going to be then? Let's see here. I think about things like 200. Is 200 the least? No, 200 is not a multiple of 80, is it? How about 400? Is 400 a multiple of 80? It is. Is it a multiple of 100? Well, it is. So I think 400 is the answer. Now, how does that relate to these factors? So to get a common multiple, we need what? At least 2 2s and at least 2 5s, right? So let me put it this way. This one says at least 4 2s, right? And at least 1 5. From the second one, I need at least 2 2s and at least 2 5s, right? So if you think about this, we need all of these conditions to be met for the least common multiple. So the way that can happen, well, if we have at least 4 2s, right, we automatically satisfy at least 2 2s, right? So the least common multiple should have at least 4 2s. So we're going to do this one and this one, because if we satisfy these two circle conditions, we ought to automatically have at least 1 5 and at least 2 2s. So what does that give us? Well, 400 is exactly 2 times 2 times 2 times 2 times 5, right? So these guys right here are 100, and that's 4 times 100, which is 400. So 400 is the LCM. So let's see, to put it into words, you look at the prime factorizations of the numbers, and you pick the largest number of prime factors that appears for each prime factor, and you keep that for each prime factor that you see. Now, there's a way to do this with something called a factor tree or something, right? But honestly, I have not taught elementary school math, so I don't know that. The way I figure out LCM is just to think about it and try multiples of the number until I find one that it meets. That's how I actually think through this. Anyway, don't worry so much about the numerical examples. Again, we could use a calculator. All right, so now that we figured out the LCM is 400, right? How do we get this? This is 13 over 80. And to get to 400, I multiply 80 by 5, right? And to get to 100, I multiply 100 by 4. So I multiply by 4 over 4. I multiply by 5 over 5. Why am I doing that? There are two things, basic things we can do in algebra, right? We can add 0, and we can multiply by 1. A lot of the steps are just that. Creative ways of adding 0 or multiplying by 1. 5 over 5 is 1, right? 4 over 4 is 1. All right, so what do we got? We've got 65 over 400. 4 times 7 is 40 plus 28, I think 68 over 400. So what do we got? 133 over 400. There you go. You're like, well, that was a lot of trouble. Wouldn't it have been simpler to just multiply 13 by 100 and 17 by 80 and then reduce? Yeah, maybe. I think if I was in elementary school, I probably would have just done that. So you have choices here. But me see if I can find a less complicated example that's a little bit easier on you guys. Let's see here. How about 3/20 plus 11/36. So what's the common factor here? They both have 2 in them, right? So actually, let me make this a little bit simpler on us. Let's put a 40 here instead. That's a little easier. That's actually the kind of thing I wanted to illustrate. How about this? So what should we do? We should keep the 40, right? Because we can convert the 20ths to 40ths by doing what? Multiplying by 2 over 2, right? We can't just multiply by 2. We have to multiply by 2 over 2, because we can only multiply by 1 unless we're going to change things, you know? Now you can multiply an equation by 2, all right? But if we're just looking at this expression, this particular number, I'm going to multiply by 1, otherwise I change it. But there you go. We've got 6/40 plus 11/40, which is 17/40, all right? Okay, so I hope that's a quick but perhaps, I'm hoping, helpful review of how we work with fractions numerically. Let's talk about rational expressions. So let me just give you a definition, all right? So I'll follow the book here, and more or less what they start with, although they may not give you this definition, I'm going to. If P of x and Q of x are polynomials, all right, then f of x equal to P of x over Q of x is a rational function. All right. And then we say P of x over Q of x is a rational expression. So if you just think about the formula for f of x on its own and don't think about it as a function, we call it a rational expression. We'll be doing a lot of work with rational expressions. Now, we talked about functions before. What are the sort of 2 interesting basic questions about a function that you ask? How about, like, well, 3 really, right? What's its rule? What's its domain? What's its range? All right? I'm going to set aside the question of range until later. That's a harder question. But the question of domain, that's pretty easy. Let's look at some examples. How do we figure out how to find the domain? Of rational function. All right, so example 1, suppose we had f of x equals to 3x plus 2 divided by x minus 8. What's the domain of f of x? So to figure out the domain, we have a formula, right? So the question of what the domain is the question of where does that formula break down? So what's the problem with that formula? It's got division, right? What can we not divide by? We can divide by anything except for one thing, right? We cannot divide by 0, right? So we need x minus 8 not equal to 0, right? So we have to throw out 8. So the domain of f of x here is the real numbers with the number 8 removed. Let me express that in interval notation. I usually ask you guys for interval notation, don't I? So minus infinity to 8, unioned with 8 to infinity. So we just have to exclude 8. What about the numerator, 3x plus 2? Did it matter? It did not matter. All right. So the numerator doesn't really play a role in deciding what the domain is. It's all about the denominator. Example 2. Let's see here. What if we had f of x equals to 3x plus 17 divided by x squared plus 4x plus 5? What did we learn in the last part of the course? We learned how to complete the square, right? So we can complete the square on that denominator. I'm going to go ahead and do that. So we've got 3x plus 17 divided by x plus 2 quantity squared plus 1. I'll put it in red below because I know you guys are going to have questions. So what I just did is x squared plus 4x plus 5 is x plus 2 squared minus 2 squared, which is 4, plus 5, right? So in red, that's completing the square. Just on the denominator polynomial, right? Now, why would I do that? I'm doing that so you can answer the question, is the denominator ever 0? Why not? What's the smallest the denominators can be? This 1, you can't get rid of that. Always this plus 1, right? X plus 2, well, the smallest, that could be a 0, right? When x equals minus 2, that's 0. So if you think through it, the denominator is at least 1. It's never 0. So what's the domain of this function? So since x squared plus 4x plus 5 is not equal to 0 for all x in the real numbers, right? The domain of this one is the whole real numbers. Hooray. So unlike the top one, this one doesn't even have a restriction. Now you might be saying to yourself, wait a minute, you mean to tell me that factoring still matters? Yes, factoring still matters. Factoring matters a lot. Factoring is a lot of how we'll be either successful or not in this next couple chapters, because factoring is still with us. Here's another one. What's the domain of this rational function? Now, I wouldn't recommend completing the square in the denominator this time. There's something easier we could do, right? Can you factor the denominator here? Yes? How would you factor it? Right. And this x to the 10th plus 27 just stays up there. I heard an x plus 1, x plus 2. I'll buy that. So, you know, what is not allowed here? We need x plus 1 times x plus 2 not equal to 0. So x equals to minus 1 and x equals to minus 2 are forbidden. Right? They are no allowed. We cannot have those. So what's the domain? I'll write it in interval notation. the domain here. What was that? Did somebody leave or somebody go? I'm curious. They left the scene of the crime. So what's the domain? We need to exclude -1 and -2. So in interval notation, that looks like -infinity to -2, union -2 to -1, union -1 to infinity. So there's the domain in this case. We got to exclude those 2 points, plus or minus, -1 and -2. So, did you guys get the idea? I think we should move on unless there's more questions about these. You don't get the idea? You want to see another one? You want to see another one? All right. Example 4. Suppose we had f of x equal to 3x minus 9 over 2x plus 7. What's the domain? So we must not allow division by 0. So we need 2x plus 7 not equal to 0 for the formula above. To work, let's say. And by work, I just mean the laws of arithmetic don't break down, right? Like, we cannot divide by 0. So when is 2x plus 7 not equal to, equal to 0? So 2x plus 7 equals to 0 tells me what? It tells me 2x is minus 7, right? And then divide both sides by 2, what do you got? So there we go. So this we must exclude this. So we want to exclude minus 7/2, so we do this. That's the domain in this case. We just take the real numbers and throw out minus 7/2. Oh, right. So when is x plus 1 times x plus 2 equal to 0? Remember? So if we have x plus 1 as a factor, that means that minus 1 is the 0. It's that interplay between the factor and the 0. It flips over like that. -7. Well, it is negative. The whole thing's negative. I mean, I don't know how to answer your question. So what I'm trying to say is minus 7 over 2, right? Okay. You're good, but I'm just pointing out that these are all equal. Like you could write it any one of those ways. They're all the same number. Every one of those is minus 3.5 if you want to think about it in terms of a decimal. You can put the minus any one of those 3 places. You can even throw in a parentheses if you want, for good measure. But okay, so let's see here. Let's talk about simplification and multiplication of rational expressions. All right. So essentially, at the moment, I've looked at how to do like the beginning problems in section 5.1. So essentially problems 1 through 12 in your textbook, which you guys have agreed you don't read. Just kidding. All of the problems in my math lab refer to textbook numbers, right? So I'm just saying what we've done in class right now corresponds roughly to like problems 1 through 12 in section 5.1. I'm now moving on to the later problems in 5.1, all right? So let's Now we're going to look at some how to manipulate rational expressions. So example 5, let's say. Suppose we had x plus 8 over x minus 7. All right, and we're multiplying that by x over x. How's that go? Now, in your textbook, they don't have the parentheses. I like to put parentheses in. I am a big fan of parentheses, just to emphasize the order of operations, so to speak. But just like we multiply numbers, top to the top and bottom to the bottom, same thing here. So this is x plus 8 times x divided by x minus 7 times x. All right? And so this would be, x squared plus 8x divided by x squared minus 7x. Right. Is that the end? Yeah. And this one. Now, the larger point is that these are equal, and I would say this. We can say a little bit more. If x is not equal to 0, then x squared plus 8x over x squared minus 7x is actually equal to what? X plus 8 over x minus 7. I mean, that is true. They're awful rowdy over there, aren't they? They must have been inspired by those people singing in the hallway, whoever those people were. But, well, you guys remember when before we factored, we multiplied, right? That's kind of what we're doing at the moment. We're talking about how to multiply fractions of polynomials. We will soon return to the question of how to break them into pieces, Let me look at another example here. Pick one from your textbook. So the instructions here are to not simplify. This one's actually good. We have minus 1 over minus 1 times 2 minus y squared over 8 minus y. And then let me write the next example here before I put the book down. Q minus 5 over q plus 3 times q plus 5 over q plus 5. We're supposed to multiply. All right, so the first one, we have minus 2 minus y squared, right? Divided by minus 8 minus y. So what happens? When you distribute the minus through, what happens? We get minus 2, and we get minus a minus, which is plus, right? So minus 2 plus y squared divided by minus 8 plus y. For reasons of style, I have to write, I don't know, I just don't like putting the minus first. I prefer to write it like this. Y squared minus 2 over y minus 8. I feel better writing the answer like that. It's silly, but there it is. Now, the next one, what do we got? we've got q minus 5. I'm just going to go ahead and do it because I'm out of board here. But what's q minus 5 times q plus 5? It's q squared minus 25, right? And how about downstairs? We've got q squared plus 3 plus 5, q squared plus 8q. 3 times 5 is 15. So again, just like the numerical examples at the start, we're multiplying the top times the top and the bottom times the bottom. That's how we multiply. And I'm just not simplifying here. If I was simplifying, I wouldn't, basically, if I was simplifying, I wouldn't do the multiplication, you know? Like, the simplification here is just q minus 5 over q plus 3, truth be told. But, all right, let's start doing some simplification problems. I think we need to do that. So here we're told to simplify. (15) y to the 5th divided by 5y to the 4th. What do you think about that one? Example 9, we have, let's say, 12x minus 15 over 21. Example 10, we'll look at t squared minus 16 divided by t squared minus 8t plus 16. Example 11, we will look at w cubed minus z cubed divided by w squared minus z squared. So in every one of these, our goal is to simplify. So how do we, so the simplification, let's see here how to think about this. What if we have y to the 5th over y to the 4th, what does that leave us? 1y, right? Now if you want me to, I could kind of show work for that, but I think it's better if I just write down the answer in this one. I think if I show work, I'm going to make it more complicated than it needs to be. 15 divided by 5 is what? 3. Y to the 5th divided by y to the 4th is just y. So the answer is 3y. If you want me to show you how to think about this, like more systematically, write it over here. Y to the 5th over y to the 4th. That is y to the 5 minus 4. That's how that works, okay? Which is y to the 1, which is just y. Yeah, if we times, we add them. If we divide, we subtract them. And beware of like negative things in the denominator. They become, you know, what I'm trying to say is if I had something like y cubed over y to the minus 2, that's y to the 3 minus a minus 2, yeah? So there's also that to watch out for. But how about this 12x minus 15? I suggest what we do here is factor out a 3. So that's 4x minus 5, right? And 21 is 3 times 7, right? So we can cancel the 3's. And we're left with 4x minus 5 over 7. That's about as simple as I can make it. There you go. There's example 9. Example 10. Once you guys have got that one. So we, in order to simplify rational expressions, often we need to factor them in order to see how to simplify them, right? How do you factor t squared minus 16? That's a difference of squares, isn't it? 16 is 4 squared. So remember the pattern. A squared minus b squared is a plus b times a minus b, right? Difference of squares. So the numerator, we've got t plus 4 times t minus 4. How about the denominator? Does that factor? I'll write a template for you. You got your t, you got your t. What do you want to put? 16 is what? It's 4 times 4, right? But if I put plus 4 and plus 4 there, multiply it out, I get an 8t. Minus and minus, that's right. So we put minus 4, minus 4. In other words, the denominator is t minus 4 squared. Aha, look, so we found the commonality between the numerator and the denominator. What is it? It is t minus 4, right? So we cancel these dudes, and what we got? T plus 4 over t minus 4, and that is the answer. So the instructions to these problems is to simplify the expression, right? In contrast, these examples over here, examples 5 and 6, the instructions were just to multiply the expressions and do not simplify. They had different instructions. This w cubed minus z cubed, I'm going to factor this one for you guys because it's kind of tricky. So this one's w minus z, and that's w squared plus wz plus z cubed, z squared rather. So this is one of those special form trinomial formulas that we had, right? And this is one of those places where, you know, if I didn't give you guys the ability to bring a page of notes to the test, like I probably wouldn't put that on the test. You do realize that if you didn't have a page of notes, the test is easier. If you did not have a page of notes, then I would make the test easier. That's true. The great debate begins. All right, so I'm just joking. We've already chosen our ninja way here. So of course the denominator factors is w plus z, w minus z. It's done by difference of squares. Do you see any common factor there? I do. See it? W minus z and w minus z. Very good. So answer is w squared plus wz plus z squared divided by w plus z. All right. Another example. We're asked to multiply and simplify. So here we have x to the 4th divided by 3x plus 6 times 5x plus 10 divided by 5x to the 7th. Now, although the book says multiply and simplify, it maybe is better instructions, a kinder set of instructions to say simplify then multiply. Because simplify then multiply might be easier. What do I mean by that? I mean, well, see this? Let me rewrite it this way. So this is x to the 4th times 5x plus 10, right? Divided by 5x to the 7th times 3x plus 6, yeah? So what is x to the 4th over x to the 7th equal to? I'll write it over here. X to the 4th over x to the 7th is equal to 1 over x to the 7 minus 4. You could also do that, by the way. You're like, I would rather put it in the numerator. I mean, whatever floats your boat. This is the same as x to the 4 minus 7 if you prefer to do it that way. You want to do it that way? All right, fine. We're going to agree on the answer. This is x to the minus 3, which is 1 over x cubed, full circle. Well, at the moment, I'm just focusing on just this piece of it, the x to the 4th over x to the 7th. We'll come back to the whole fractions. I've changed colors just to do the x part. So using what I did in red, x to the 4th over x to the 7th simplifies as 1 over 5x cubed. We can factor a 5 out of 5x plus 10, right? 5 times what? Times x plus 2, right? And we can factor a 3 out of the x plus 6, can't we? What? Factor 3 out of the 3x plus 6, what do we have? We have 3 times x plus, plus 2. Oh, look at that. Those wascally wabbits. See here. So the 5's cancel, the x plus 2's cancel, and what are we left with? Yeah, 1 over, we got a 3 and an x cubed left over. That's pretty neat. I mean, if you look at this, look at what we started with, right? Does it look like that's 1 over 3 times x cubed? It sure doesn't, but that's what it is. Now, to be fair, if we're thinking about plugging numbers into this, there's one number we're not allowed to plug in. 0. Well, 0, that's true. We can't plug in 0, but there's another number, which you can't see from this, but you could see from up here or maybe up here best. Notice minus 2. Minus 2 is also not allowed before the simplifications, but minus 2 you could plug into the boxed answer. What I'm trying to say is in the process of doing simplifications, you can change the domain of the rational expression. Simplification can change domain. But I think I'm making a kind of, we'll come back to that idea later if we need to. How about this? We've got y squared minus 16 over 2y plus 6. We're supposed to multiply that by y plus 3 over y minus 4. So again, I really think simplify then multiply is the right instructions. So the y squared minus 16 factors into y plus 4 times y minus 4. You still got your y plus 3 up there, right? Can we factor, we can pull a 2 out from that 2y plus 6, can't we? Something exciting going on in that other room. All right, so we can factor a 2 out of this. So it's 2 times what? Y plus 3, very good. And what do we have left in the denominator? Still got that y minus 4. So what cancels? Y minus 4? Yeah, y minus 4 cancels. The y plus 3 cancels. And we're just left with y plus 4 over 2. All right.
How come we don't divide 4 and 2?
Well, you could if you wanted to. This would also be equal to y over 2 plus 4 over 2, which would be 1/2 y plus 2. That's another way to write the answer. Now, you can't just cancel the 4 and the 2 to leave y plus 2. That is not true. You have to have a multiple of 2 on both terms to cancel the 2. Yeah. I'll buy it. All right, so next instruction is to divide and simplify. Divide and simplify. So I'll write these out. Now, your textbook has this, you won't see this on my test, all right? Like, I'll just warn you. I don't use the divide symbols in an algebra test because this is university. All right, so 6x plus 12 divided by x. And what I mean by is this symbol. This symbol right here, like, that is not a symbol we use in here so much. So here's the way this problem will appear on your test if it were to happen. On your test, it would look like this. It would look something like 6x plus 12 divided by x divided by x plus 2 divided by x cubed. So you always use the compound fraction, or some people call it complex fraction notation. Yeah, like this. I'm just warning you, in your homework and in the textbook, they use the division symbol. All right, so I'm warning you, these mean the same thing. Now, how do we work this problem? We use remember a thing I wrote about A, B, C, D earlier? So we use that pattern. A over B over C over D is AD over BC. So this is just 6x plus 12 times x cubed divided by x plus 2 times x. And now we can simplify, just like we did the previous ones. Can you factor anything out of 6x plus 12? How about a 6, right? 6 times x plus what? 2, right? And we've got x cubed divided by x plus 2. I'm not even really simplifying here just yet. So what do we get? We've got 6. The x plus 2 is canceled, right? And what's x cubed over x? It is just x squared. Thank you. There it is. Mm-hmm. You got it. One more of these, and then we'll move on. Example 15. We could have 25x squared minus 4 divided by x squared minus 9, all divided by 5x minus 2 divided by x plus 3. How do we deal with this guy? So we do 25x squared minus 4 times x plus 3 and 5x minus 2 times x squared minus 9. So, all right, this is 5x plus 2 times 5x minus 2 times x plus 3 divided by 5x minus 2 times x plus 3 times x minus 3. As I was warning, factoring still matters. Got to be able to factor. If you don't know how to factor yet, you really need to see me or see a tutor or something, spend time on it. So